this lab, the relationship between position and time was explored by using a passport motion sensor and Pascal capsule software. The theory of a position-time graph is important in physics as it reveals how the position of an object changes as time elapses and connects this theory with different kinds of emotions. A motion sensor uses waves to project off a moving object and back to the sensor to calculate and display the object's new position as it moves through time. Our team was able to study and understand graphs displaying different position-time relationships, predict what types of motions would be required to generate the graphs, and then actually move an object to mimic and move along the same kinds of trajectories and movements as demonstrated by the position-time graphs provided in class.
Figure 1 shows the materials and the setup that we used in this experiment. So looking to the left of the image, we have the capstone program, which basically was to record our graphs based on the motion detected. And next to it on the right, we have our laptop, which we used to reference the graphs that we were going to recreate in this lab. And next to that on the right, we have the water bottle, which is the object we used to provide the motion captured by the sensor. And then in the middle of the screen, the small blue object on the table is the passport motion sensor, which is used to capture and sense the motion by the water bottle. And then on the bottom of the image, we have a phone, which was just used to record the experiment and to take pictures of the graphs at the end of each lab. And this was basically all the material and equipment that we used for this lab.
Here you can see our first attempt at trying to replicate the graphs using the sensor. And here is our second attempt using a water bottle to yet again replicate the graphs. For graph 1, the graph is in a position versus time graph, so the vertical axis shows position and the horizontal axis shows time. The slope of the line tells us how the object is moving. When the line slopes up, the object is moving away from the sensor. When it slopes down, the object is moving toward the sensor. A steeper slope means faster motion, and a flat line means the object is still. Starting with my region 1, the line slopes upwards slightly, which means this object is going away at a slow pace. The slope is gentle, which shows the object is moving away steadily, but not very fast. The motion is smooth, so the speed is mostly constant. For region 2, where the line becomes almost completely flat, this represents that the object was being still and was just still. Since the position does not change over time, the object is not moving at all. It says at the same distance from the sensor. For the next region, the line slopes downward sharply. This shows the object is going toward the sensor at a fast pace. The steep downward slope means the object that I had was moving quickly back towards the sensor. After that, in region 3, the line slopes upward more steeply than before. According to the key, this represents the object going away at a fast pace. The steeper upward slope shows an increase in speed compared to region 1. Finally, the graph returns to region 2 where the line flattens again, which means the object becomes still and steady once more, staying at a constant position until the end of the graph.
The graph we created, which is graph 2 depicted, was in a position versus time graph. So the x-axis represents the time that went by in seconds, and the y-axis was the position of the object relative to the motion sensor in meters. And basically, in the first phase of the graph, where it has the 2 numeral, that is where the object was staying steady. In this case, it was a water bottle. And in the next phase, where it has the 1 numeral, that meant that the water bottle is going at a slow pace, going away at a slow pace from the motion sensor. In the next section, where it has a 3 numeral, the water bottle was going away from the motion sensor at a faster pace. And then in the fourth phase, the water bottle was going towards the motion sensor at a fast pace. And then from there, the water bottle went away from the motion sensor at a fast pace. And then from there, the water bottle stayed still as it was in the staying steady phase with the 2 numeral. And then from there, the water bottle went away from the motion sensor at a slow pace, which is the last part on the graph at the 1 numeral.
In graph 3, we can yet again see how time is in the x-axis and position is in the y-axis. For this graph, we start off going down in a negative direction. As you can see, in the key, it is going towards at a fast pace. Then we stay steady as the line is straight, and then we go again down diagonally towards a fast pace. Then we have another line going down diagonally, but this one isn't as strong as the other line, which is why it is going towards a slower pace. And then once again, we stay steady for the end of the graph.
For graph number 4, the procedure was fairly straightforward and consisted of 2 repeated motions. First, the object moved away from the sensor at a fast pace, and then it moved back towards the sensor at a fast pace. This pattern was repeated several times throughout the trial. As a result of these rapid back and forth movements, the sensor recorded sharp changes in position over shorter periods of time, which appeared as distinct spikes on the graph. These spikes match the expected pattern and closely resemble the model graphs that were provided earlier in the lab activity.
For its conclusion, in this lab, we were able to study the relationship between position and time using a passport motion sensor and Pascal capstone. The activity provided us with a clear understanding of the position time graphs that represent different options by relating the graphs to a real-life motion. Despite the difficulties our group experienced in accurately reproducing the graphs provided, this could be attributed to user error in the sensors. By zooming in our graphs, we were able to locate areas in our data that resembled the original graphs. This lab demonstrated the concepts of motion graphs to us and the difficulties that are encountered in acquiring accurate experimental data.